All right, so this lecture kicks off our discussion on rotational motion, starting with this lecture on rotational kinematics, which will actually draw a lot of equivalency from what we've learned so far in terms of describing the object's motion and how the object moves in a linear fashion. So so this lecture is on rotational kinematics. And just a reminder that when we say kinematics, we are talking about how we describe an object's motion. So in the beginning of this semester, when we were talking about how an object moving along a straight line is described in terms of its motion, we learned about its displacement, velocity, and acceleration, right? We were describing the object's motion in terms of its velocity, displacement, velocity, and acceleration. Now, when we take the object and we make it rotate, we can then describe the motion of this object in terms of angular displacement, angular velocity, and angular acceleration being the kinematic variables in the rotational motion. So in this lecture, we will define what these angular kinematic variables are and how do we calculate them and how they are equivalent to the linear displacement, velocity, and acceleration. Right. So before we define these variables, let's first just define in the context of a rotating object, the two kinds of objects that we encounter. We have one, what we call a non-rigid object, such as this pizza dough. It's a very skilled man over here. Yeah, so this is the pizza dough is a non-rigid object as opposed to, for example, some ceramic plates that are being rotated. These ceramic plates, they are what we define as rigid objects. So in the context of rotational motion, rigid objects, we define them as objects whose shape do not change as they rotate. Okay, it's quite obvious for the pizza dough, the shape is changing. So there is some deformation that we can see in a non-rigid object, whereas for rigid objects, the deformation is negligible. And since the shape doesn't change and the deformation is negligible, we can say that the relative distances between different points in the rigid object is constant. And so this will simplify, our analysis of rotating objects. So in this course, we will essentially consider only rigid objects that are rotating. Okay, right. So that, as I've said, for a rigid object, say this thing here, as it rotates about a fixed axis, which we call axis of rotation. Okay. As the rigid object rotates along a fixed axis or axis of rotation, we can see that each point will sweep the same amount of angle, theta. So here I put a string as a guide for the eye. If we use the string as the reference point, then if we rotate this rigid object, note how each point along the string will sweep the same angle theta as this rigid object rotates. And because of this angle theta being the same at each point along this rigid object, we can then define some rotational variables, rotational kinematic variables. But let's relate them, as we define them, let's relate them to their equivalent in linear or translational motion. So when we were talking about motion along a straight line, if we wanted to find the location of that object, we describe its position. When the position changes, then we have displacement. Change in displacement over time, we have velocity, and change in velocity over time, we have acceleration. Now, if we rotate the object, each location in the object will be described by some angle. Okay? Any change in angle will be called the angular displacement. And the how fast the angle changes, how fast the angular displacement changes is described by what we call angular velocity, and how fast angular velocity changes is described by angular acceleration. So if we look at this table, these kinematic variables are sort of equivalent. We just use, angle and angular to distinguish rotational motion from linear or translational motion, right? Okay, so angle, we use the symbol theta to describe the location or position of the rigid object. The angular displacement will be the change in theta. Angular velocity, we use this symbol, which we call, it's a Greek symbol read as omega. Okay, so the omega is the rate of change of angular displacement. We will see, we will define as average angular velocity and instantaneous angular velocity. And then rate of change of angular velocities, angular acceleration, we'll use this symbol, which we call alpha, this Greek symbol alpha, to designate angular acceleration. Again, we will define average angular acceleration and instantaneous angular acceleration. Right. Okay, so laying all these terms now, we are now in a good position to talk about each of them. Let's start with the angular displacement delta theta. So how do we define angular displacement delta theta? So so let's consider this object that's rotating. Okay, so you have a rotating object. It has a radius r relative to the fixed axis of rotation, right? So each point along this object can be defined by this position angle theta. Right, so let's say initially this position has an angle theta. After some time, with some arc length s, after some time when the object rotates, so that we're now looking at this point here, the position would have changed by delta theta. So delta theta here is how much the angle changed over some period of time. We call this change the angular displacement. We measure the angular displacement in terms of radians. Okay, so that the unit, the SI unit we will use for angular displacement is radians. And we can convert radians to degrees using, the relationship where pi radians is equal to 180 degrees, or 2 pi radians equals 360 degrees. And so 1 radians equals 180 over pi. So this will be the conversion factor for degrees to radians. 1 revolution is, of course, 360 degrees or 2 pi radians. Right? So angular displacement, it's measured in terms of the angle theta, the change in the position theta or delta theta. Okay. Angular velocity, it's how fast this position changes. So if in linear motion, we define velocity as displacement over time, right? So in angular velocity, it's the same principle. It's the displacement over time, but this time it's angular displacement over time. Delta theta, we've seen to be angular displacement. So it's how fast the position changes. If we're looking at time interval delta theta, so delta theta is the interval for which the position angle theta changed, then we are talking about average velocity. So average angular velocity takes the interval, a finite interval time it takes to change the position theta. If we let the time approach 0, such that this limit of delta theta approaching 0 means that we are making the time interval smaller and smaller, such that we approach just a single time, then we will now talk about instantaneous angular velocity. Yeah, instantaneous meaning the angular velocity at a particular instant of time, right? At a single time, we want to find the angular velocity at. Okay, so we have this limit of the time interval delta t approaching 0 means that this delta theta becomes a derivative. So if you want to get the instantaneous angular velocity, then we get the derivative of the position theta with respect to time. All right. Okay, sign conventions. As before, when we talked about velocity, velocity is a vector quantity. So we have to indicate the direction. And the convention we used was to the right and upwards is positive velocity, right? If the object is moving along a straight line to the right, we say that its velocity is positive. Now for rotational motion, it will now be just a question of whether the object is rotating clockwise or anti-clockwise. So we'll define a anti-clockwise rotation to be positive, to have a positive angular velocity, and a clockwise rotation to have a negative angular velocity. Okay. To see why, so let's say you have this object here and say it's rotating in the, what's this, anti-clockwise direction. So if you have an object rotating in the anti-clockwise direction here, to find the direction of the angular velocity, you take your fingers and curl them in the direction of rotation. So if the object is rotating in the anti-clockwise direction, your fingers curl anti-clockwise, and your thumb points in the direction of the angular velocity. All right, so your thumb here is pointing upwards, which we have designated before to be positive, and that's why anti-clockwise rotation gives you a positive angular velocity. Okay. On the other hand, clockwise rotation, right? So clockwise rotation, you again take your fingers, curl them in the direction of the rotation. Notice how your thumb will naturally point in the downward direction. Okay. And so we have this downward, of course, is what we designated to be negative direction. So we have this convention of anti-clockwise rotation giving us a positive angular velocity, and clockwise rotation giving us a negative angular velocity. Right. Okay, in terms of units, so the unit for angular velocity, I'll just put it here. Yeah. So the unit for angular velocity, it's defined, right, delta theta over delta t. The unit for displacement, angular displacement, is radians, and the unit for time is seconds. So then the unit for angular velocity is radians per second. Sometimes you will see in some textbooks, they will just use the unit seconds. 1 over second or second to the minus 1. It's the radians is sort of omitted, but yeah, I think it's good practice to put radians per second as the unit, because it reminds you that angles should be measured in radians. The angular displacement should be measured in radians. Okay. There is, though, an alternative unit for angular velocity, which is the revolutions per minute, or RPM. And we I think we encountered RPM when we talked about uniform circular motion before. So RPM means revolutions per minute. You can already sort of see why it's also angular velocity, because you have here the displacement, angular displacement, given in how many revolutions there were per unit time, except that, you know, it's not the SI or standard unit for angular velocity, because for one, time is measured in minutes and the angular displacement is measured in revolutions. But then we need to be able to convert revolutions per minute to radians per second. So this slide simply defines the relationship between revolutions per minute to radians per second. So if we define some time, period, capital T, to be the time for one revolution, then the quantity frequency, which is defined as the number of revolutions per unit time, is defined as the inverse of the period. So we can see that frequency is measured as 1/seconds or hertz. The SI unit for frequency is hertz. If we look at this mathematical definition for frequency, it's 1/period. Period is measured in time. So in terms of units, this is 1/seconds. And so frequency has a unit of hertz or 1/seconds. This also tells us that 1 hertz is equal to 1 revolution per second, because the period is the time it takes for 1 revolution. So hertz equals 1 revolution per second, and that's where the RPM comes in. Okay. It's just, and I think RPM is usually what's used in the industry. It's just because minutes is easier to measure than seconds, but we need to be able to convert RPM to radians per second. We can see the conversion factor from here. If we sort out the angular displacement being 1 revolution is equal to 2 pi radians. Okay, one circle, one trip around a circle gives you 2 pi radians. So 1 revolution is equal to 2 pi radians, and the time it takes for 1 revolution equals the period T. So your angular displacement can also be defined as 2 pi f, which is sometimes measured as revolutions per minute. Okay, right. But practically, how do we do this? How do we convert revolutions per minute to radians per second? Let's look at this example to see how it's done. So here you have a computer hard drive. The platter of the computer hard drive rotates at 7,200 RPM. What is its angular velocity in radians per second? This is actually just a conversion problem. So we want 720 RPM. How much is this in radians per second? Okay, so we know that 1 revolution, so to convert something, we need conversion factors, right? So the conversion factors, 1 revolution is 2 pi radians. And of course, 1 minute is 60 seconds. Okay. Right. So if we convert 7,200 revolutions per minute, okay, then that will be 7,200. We don't want revolutions, we want radians. So we replace revolutions by the conversion factor. 1 revolution is 2 pi radians. So that's 2 pi radians divided by minute. We don't want minute, we want seconds, but 1 minute is equal to 60 seconds. Okay. So then this gives us the expected answer as shown here, 754 radians per second. Radians per second is the unit for angular velocity. Okay, and so revolutions per minute, or RPM, is also referring to angular velocity, just not in the standard or SI unit that you want. Yeah.
You can also say rads -1.
Yes, yeah, you can also say rad second -1, or another acceptable unit is just second to the -1. Yeah. Cool. All right, so that's angular velocity. So we've defined now angular displacement, delta theta, how the angle changes, and then angular velocity, delta theta over time, how the theta changes over time. Now, angular acceleration, when we talked about acceleration, it's change in velocity over time, right? Delta V over delta T. So when we just put angular, we're looking at rotating objects. It's therefore the change in angular velocity over change in time. How fast the angular velocity changes over a time interval delta T. So again, if we're looking at a finite time interval delta T, then what we are measuring is average angular acceleration. Okay? How quickly the angular velocity changes over a finite time interval gives us the angular acceleration. If we let the time interval approach 0, so in the limit where we are making the time interval smaller and smaller, such that we are just approaching a single time, then we are looking at instantaneous angular acceleration. And the finite delta omega over delta T becomes the derivative of omega with respect to time, or derivative of angular velocity with respect to time. Okay. Right. And if we recall also that omega, the instantaneous angular velocity is equal to d theta over dt. Okay, then the angular acceleration will be the second derivative of position theta with respect to time. Right. In terms of units, if we look at the unit from the definition of angular acceleration, which is delta omega over delta t, this will be the unit of the angular velocity. Right. The unit for angular velocity is radians per second. So you have radians per second divided by second will give you radians per second squared. Again, it's equivalent again to that meters per second squared, right? But instead of meters, we're using radians, because instead of linear distance, we're looking at angle theta. Okay. In terms of direction for the angular acceleration, because it's also a vector quantity, just like linear acceleration is, we define that if the direction of rotation is anti-clockwise, okay, what's the direction of the angular acceleration, angular velocity again in this case? Do you remember? Yeah, curl your fingers in the direction of the rotation, and so your angular velocity will be downwards. Now, the direction of angular acceleration, it depends on whether the object is slowing down or speeding up, whether the rotation is slowing down or speeding up. If the rotation is speeding up, then the angular acceleration should be in the same direction as the angular velocity. And if the object is slowing down, then the angular acceleration should be opposite the direction of the angular velocity. Okay, so sort of trying to determine the sign of angular acceleration, whether it's positive or negative, you sort of have to look at the context of the problem and see whether the rotation is speeding up or slowing down. Slowing down will give you a negative angular acceleration. Oh, well, if your angular, yeah, slowing down will give you an opposite direction to the angular velocity. So it's a two-step process now. So first, determine whether your angular velocity is positive or negative. Remember that angular velocity is positive if anti-clockwise rotation and negative if clockwise rotation. That's the first step. Determine the direction of your angular velocity. Once you've determined the direction of your angular velocity, look at the problem and the context, whether the rotation is speeding up or slowing down. Okay. If it's slowing down, then just the sign of your angular acceleration will be opposite the determined sign of angular velocity. If it's speeding up, then the signs will be the same for angular velocity and angular acceleration. Okay, right. So a lot of equivalency between linear motion, linear kinematics, and rotational kinematics. So it will also make sense that the equations, the kinematic equations that we used for linear or translational kinematics can be applicable to rotational kinematics, except that this time the object is rotating instead of moving in a straight line. So how do we relate? What's the equivalent rotational kinematics equations? Okay, so on this side here, we have the translational or linear kinematic equations, right? So the acceleration becomes angular acceleration. And as usual, these equations hold if the angular acceleration is constant. But in this course, we'll only consider constant angular acceleration anyway. Okay, so notice how the position x or displacement x is replaced by the angle theta or the angular displacement delta theta. Okay, the initial velocity v0, it's replaced by initial angular velocity. Acceleration a is replaced by angular acceleration alpha. Time is still time, right? Whether the object's rotating or moving in a straight line, it's still the same time. Okay. So it's still the same, all the same kinematic equations, just the variables will change to relate to rotational kinematic variables. Right. Okay, so then also all the techniques that we learned in solving kinematic problems, the worded kinematic problems, will also be applicable in rotational motion. And so let's test how we apply these rotational kinematic equations in worded problems. So let's consider this example here. You have a centrifuge. Okay, the centrifuge is a device that rotates at a very fast speed. Here it's used in food processing to refine vegetable oils. The centrifuge rotor is accelerated from rest to 20,000 RPM in 30 seconds. So it starts from rest and then you turn it on, the centrifuge is turned on. It then goes from rest to 20,000 RPM in 30 seconds. What is the rotor's angular acceleration and how many revolutions will the centrifuge have over this acceleration period, meaning over 30 seconds. Okay, the angular kinematic equations are shown here. So I'll give you a couple of minutes to sort of think about this problem and maybe even start working at the solution, working on the solution. Okay, I'll just turn this over here, but the problem is still there and the rotational kinematic equations are still there. So as before, it's always useful to write down what we know, what's given in the problem. Okay, just maybe just think about rotational motion now. And so you have the centrifuge is accelerated from rest. From rest means initial angular velocity should be 0. It's not rotating initially. Yeah, so the angular velocity should be 0. And then you have a time of 30 seconds. Right, and then it's accelerated to 20,000 RPM. So RPM, revolutions per minute. That gives the unit, gives you a clue. This should be the final angular velocity of the rotor, which is 20,000 RPM. Right, before you do anything, convert your units to SI or standard units. So that means RPM should be converted to radians per second. You know, 1 revolution is equal to 2 pi radians, and 1 minute equals 60 seconds. All right, so 20,000 RPM, 20,000 revolutions per minute. This will be equal to 20,000 times 2 pi radians divided by 60 seconds. Okay. That gives you 2,094.4 radians per second. Okay, so you now have their initial angular velocity omega naught, final angular velocity omega f, and time t. Now looking at your kinematic equations, rotational kinematic equations, we don't know theta. Theta is the angular displacement, or how many revolutions. Right, so any equation that has theta can't be used. So there's only actually one possible equation to use. We want angular acceleration, which is this alpha here. Right, so we have omega is equal to omega naught plus alpha t. The initial angular velocity is 0, so this one is 0. Therefore, omega is equal to alpha t, or you can then find the angular acceleration alpha to be omega over t, 2094.4 radians per second divided by 30 seconds. Right, gives you an angular acceleration of 69.8, or about 70 radians per second. Second squared, sorry, for acceleration. All right, any question about this solution here? Yeah? Yeah. So it's really just exactly like linear kinematics, except that you just have to sort of change the way you think of in terms of along a straight line, it's now rotating. And so the variables are rotational kinematic variables. Right, the second question, through how many revolutions will the centrifuge turn during its acceleration period? So the acceleration period, the angular acceleration we've calculated previously was over a time interval of 30 seconds. And how many revolutions? This means theta. What's the essentially the angular displacement, or how many revolutions did you have? So you have time. So what you have is time, 30 seconds, initial angular velocity 0, final angular velocity. You converted as to 29.4 radians per second. Okay, right, and you want to find theta. Yeah, of course, you've calculated alpha, the angular acceleration from the previous question. But if you want to be sure, and if it is possible to use any of these equations to solve for theta without using alpha, then that will be a safer solution. Yeah. So, so say, is there any possible equation that you can use here to solve for theta without knowing alpha? Well, there is. So this last equation here can be used to solve for theta without knowing alpha. If you know alpha, of course, then you can use essentially any equation here. But just on the safety side, we'll use the one without alpha. But we'll see. It will. So we'll see how that goes. So 1/2 omega plus omega naught times t. All right. The initial angular velocity 0. Again, initially the centrifuge is not rotating, so omega naught is equal to 0. So this is just now a direct substitution of everything. 1/2 times 2094.4 radians per second times the time 30 seconds. Right. This should give you a theta of about 5 times 10 to the 3 radians. No, it's not 5 times 10 to the 3 radians. It will give you some value in radians. But in my solution, I did not convert to radians, so that will give you. So anyone? 31,000 radians. Okay. What's being asked is revolutions. So how many revolutions you'll still need to convert this to revolutions. So convert this to revolutions. 1 revolution is 2 pi radians. Okay, so if you do 31/10 divided by 2 times pi, here is my decimal point. Yeah, this will give you about rounded to 5 times 10 to the 3 revolutions. So equivalently, you can also solve this without converting. So if you did theta is equal to 1/2 omega t without converting your omega, so your omega is 20,000 RPM. So that's revolutions per minute times time 30 seconds. But then you have to convert your minutes to seconds. So that will be an extra dividing by 60 seconds to convert minutes to seconds. You will still get something like 5 times 10 to the 3 revolutions. Okay. Did anyone try to use the alpha that was calculated from before to find theta? It should add up to the same. So say, for example, which equation here? So maybe let's use the first equation. If you use the first equation, say this one, to find theta, omega naught t plus 1/2 alpha t squared, okay, omega naught is 0, so this whole thing is equal to 0. You'll have 1/2 times the alpha that we found from before was around 70 radians per second squared. So 70 radians per second squared times 30 seconds squared. Right? This would give you somewhere close here. So that will be 70 times 30 squared times 1/2, 31,500. So some rounding radians. So some rounding there because I used 70 radians per second squared, which is the rounded angular acceleration alpha, but essentially some rounding there. But if you then convert this to revolutions per minute, this will also amount to about 5 times 10 to the 3 revolutions. Sorry, converting 31,500 radians will also give you something like 5 times 10 to the 3 revolutions. All right. Okay, so it should work. Cool. Any question about this solution here? No? Yeah, good. All right, so it's completely equivalent to linear kinematics. Okay, so just changing variables to rotational variables. But in some cases, when the object rotates, it will also have some linear components. So say, for example, a wheel or a tire, right? If we watch this again, this reference point here, as the wheel rotates, it can have some linear displacement, right? So as something rotates, it can also have some linear motion together with this rotational motion. And so let's relate the linear and rotational quantities. We know that, for every point here, each point will have the same angular motion, because we're considering rigid bodies. As we've seen, if this is your reference point here, every point will have the same angular displacement, and every point will have the same angular velocity and the same angular acceleration, but each point will have different linear motion. So the difference in linear motion depends on how far away the particle is, object is, relative to the rotation axis. If we think again of the example of a wheel that's rotating, okay, if we use this as the reference point, if you rotate this over some distance from some angle theta, then you have this corresponding linear displacement, right? But if you use a bigger wheel, a much bigger wheel, and rotate it over the same angle, a much bigger wheel will have a bigger linear displacement, right? So the linear displacement X should depend on the radius, or how big this rotating object is. Okay. So then it follows for the velocity, the linear velocity will also depend on the radius r times the angular velocity. And for the acceleration is a little bit more complicated, because there are two kinds of accelerations. You have the linear acceleration. So this tangential acceleration that's tangent to the point, and this is the end. As we learned before, if an object is undergoing circular motion, you have this radial acceleration. So this is radial acceleration, and this is tangential acceleration. So the tangential acceleration, that will depend on the radius times the angular acceleration. But for the radial acceleration, this depends on the angular velocity squared. Okay. So if we want, because there are two kinds of linear accelerations, The total linear acceleration will therefore be the sum of the tangential acceleration and the radial acceleration. Just remember that these are vectors, so you need to do vector addition for the total linear acceleration. Okay, so let's look at a conceptual example to sort of distinguish between these linear and rotational quantities. So say here you have a turntable. There are two rabbits. Bonnie sits on the outer rim. So that's Bonnie there. And Clyde sits somewhere midway between the center and the rim. Okay, and the merry-go-round makes one revolution every 2 seconds. Who has a larger linear velocity? Right, linear velocity v, that's related to angular. So as it's the same analogy as the wheel, except that this one, it's just in this axis here. So as the turntable rotates, the rabbit who has a larger radius will have a larger linear velocity. So their angular velocity is the same because at each point the change in angle is the same as they rotate together, but Bonnie being at the outer part will feel a different linear speed. Isn't it the case that when you stand in the middle of a merry-go-round, it's as if you're not going around, but if you're standing outside, then you will feel how much you're going around. Yeah. Okay, so follow up, who has the larger radial acceleration? Radial acceleration is the one that's related to radius times the angular acceleration. Or sorry, I got this wrong. This one is the one that's related to omega squared. So of course, the one with a bigger radius, located at a bigger radius, will also get the bigger radial acceleration. Okay. All right, any question about rotational kinematics in general or this lecture here? Yeah.
The last slide you said that the linear acceleration was equal to the vector addition of tangent and the radial acceleration. How do you do that if they're both like 90 degrees to each other?
Yes, that's a good question. So you will then always have an answer which has an x component and a y component. Yes. Yeah. Cool. All right, so I will leave you with some exercise questions here that you can do when you want. The solutions will be posted on stream, but this essentially ends our discussion on rotational kinematics. So have a good day, everyone.